was able, I just remembered, sorry if you tried to access it earlier, I was able to, where did that go? Oh, under chapter contents, you should now have access to the student solutions manual. So those are going to be the odd numbered problems in the textbook. I don't know how many of you all actually utilize those additional problems. I think some of our assignments take quite a bit of time to do. So anyways, it's there for you if you ever need it. Does anyone have any more questions? No? Anybody started the homework? Okay, good. A few people. All right. Well, I think that's pretty good. So no questions on the homework then? All right. Well, we'll continue with 6.3. So the first thing we looked at here in 6.3 is the general slicing method, and it really carries over to the majority of what we do in 6.3 and in 6.4. And that is this notion of, if I can just compute areas and then multiply them by a linear dimension, dy or dx, and sum all of that stuff up, then I can obtain a volume. So, that idea of working in like a lower dimension and then multiplying by a length is also, if you go on a Calc 3, you'll see that it's one of the ways to compute volumes that are underneath the surface. So, but it's always, let me work in the lower dimension with something simpler, and then multiply it by like dy or dx or dz or whatever. And so this idea that we're working with there is a little modification in 3 dimensions, but it parallels very nicely. I recognize that all of you aren't going on to Calc 3, but for those of you that are, it's worth mentioning. All right, and so what we said we had to look at was, in order to obtain a volume, we had to sum up the areas of each cross-section, and those varied from figure to figure, and then multiply them by a tiny length dy or dx. And when we added all of that stuff up, we were able to get the actual volume of that figure. So the first thing in these problems here is to determine, well, what are my cross-sections that are usually given to you, and then determine how do I compute the area of the cross-section. Here we're dealing with triangular cross-sections. So we started off by saying, all right, well, the area is half base times height. And then we said, which direction are the slices or the cross-sections running? They're running parallel to the x-axis, and so they had a little thickness dy. So then that told us, well, we need everything in terms of y. In other words, we need x equal to some function of y. Okay. So from the area function, we said we needed b and h in terms of y because of the dy here. And then that's where we started with the base. We said, well, what's the base? It's just the length of each green line that we produce throughout that figure. And the lengths of each green line is just measured by taking the right minus the left. Okay. So then we had to obtain a formula or an equation that described half of the circle in the positive and the negative sense. And that's how we ended up with 2 root 25 minus y squared for the length of all of those green pieces. Okay. So that's b in terms of y. Then we said we need h in terms of y. With the equilateral triangle, we said there is a definitive relationship between the base of an equilateral triangle and its height. And so we found that relationship. This right here is for any equilateral triangle, regardless of the base and height. And so with that, we were able to say, all right, then the height in terms of y is root 3 over 2 times its base, which we found prior to this. So there we have our root 3 over 2 times the base. And then we just simplified this. And so now we have h and the base in terms of y. And therefore, we're just going to put that back into the area function for b and h. Okay. So we'll say that we now have h and b in terms of y. To plug in the area function So then our area function, remember it's a function of y, so we'll say that our area function of y is 1/2 the base, which was, I'll do these in different colors, the base 2 times root 25 minus y squared times the height, which we said was root 3 times root 25 minus y squared. All right, were there any questions on what we've done? All right, so we'll just see if this area function simplifies. So, because we know that in order to find the volume, we have to integrate the area function. So we have the 1/2 and the 2 canceling out, and then the root 25 minus y squared times itself is just going to give us 25 minus y squared. Okay, so that gets squared. The root goes away. And then we still have that root 3 hanging out. So remember here, the volume is the integral of the area function with respect to y. So then the volume is the integral of our area function, root 3 times 25 minus y squared, dy, and y ranges from where to where?
-5 to 5.
-5 to 5. And again, those bounds were based on the original shape, which was a circle radius 5. Is everybody cool with that? -5 to 5? Okay. And usually if we can utilize symmetry, you don't have to do it, but it's easier if you can. So since our bounds on y range from -5 to 5, but this thing is symmetric with respect to the x and the y axis. So what we can do is cut this in half as far as the bounds, and then just multiply everything by 2. This is okay. It's just that you've got a -5 and a 5 to plug in. If we can go from 0 to 5 and double that, then the lower limit being 0 is always easier to plug 0 into anything than it is most other numbers. So I think at this point it's really a matter of what you prefer. So we could double half of that from 0 to 5. I think it's a good practice to get into using symmetry. Relevant to this class, once we start looking at doing calculus in polar coordinates, symmetry plays a huge role in doing that. But I don't think at this point it's absolutely necessary. All right. So any questions on where we're at? Then we'll work with this one here. I'm in the practice of always just pulling the constants out of the antiderivative and then multiplying them in later. If you want to leave them in, that's totally fine as well. So we just need to integrate 25 minus y squared with respect to y. And so we have 2 root 3, put this in brackets, 25y minus y cubed over 3, evaluated from 0 to 5. So you should get that to come out to be 500 times the square root of 3 all over 3 of the volume. So that is our volume of the figure. So I hope, like, well, with a lot of these, it's the setup that's the most difficult part in theory. I hope that's true for you all. Okay, so questions about this? Everybody feel all right with what we've done? You have 2 homework questions that are like this, and then the rest are something. Well, the rest of the section we'll talk about. Okay, then I want to look at the same approach. See if we can derive the formula for the volume of a sphere, radius capital R, and we want to slice our cross sections are parallel to the y-axis. So our cross sections are these little rectangles here. This one's true. Which means what for us? With respect to y or with respect to x? Dx. Yeah, because again, just imagine this little thin rectangle, its thickness dx. So with these problems and the ones we see moving forward, that should really be your baseline. Because if it says find the volume of this thing and you do with respect to y when you were supposed to do with respect to x, there are instances where the volume would be the same. There are instances where it wouldn't be, depending on which axis you rotated it around. But it's important for the problem itself. Even if you lucked out and did the integrated with respect to y and got the same answer, you're still going to lose points for that. So just make sure that's kind of your starting point. I'm integrating with respect to x, which means the bounds need to be in terms of x for x values, and we need to have y equals to something in terms of x dx. Does anyone remember the volume of a sphere? Maybe we can. Okay. We're capital R. Yeah, it's a volume, so it's cubed. 4/3 pi r cubed. So we can use that as a check. That's what we should get out once we do everything. Okay. And again, we're not thinking of the volume itself. We're translating down a dimension and saying, what is the area of these cross sections that I'm dealing with? So we're going to do this and translate that over here. So that's kind of the figure we're focusing on. When I slice into that, what kind of shape or figure do I get? Does everybody agree? They're all circles. All cross sections through here are circles. So cross sections are circles whose area is pi r squared. But since we're integrating with respect to x, we need r in terms of x. So we'll just focus on that red circle. You know, we're looking at it from the side. We're going to focus on that and say, well, can we determine, so, you know, like this would be a terrible representation, but my perspective is off. I get the idea. So how do we determine r in terms of x, or what is r in terms of x? Yeah, the diameter. But remember that what we're looking at here is capital R, because that's the boundary of the sphere. So you're right, it is the diameter, but the problem is, you know, whether we're looking at this particular circle or we're looking at this circle, right, those diameters vary. So the radius is half the diameter, but if you're going by that, it varies depending on where you're at throughout that circle. Okay, yeah, good. Remember, just like in the last section, when we had a vertical slice or a rectangle, we always measure that height by saying it's the top minus the bottom. So we could say that, we'll write it out. We could say that r is equal to the top function minus the bottom function. But we could also use the fact that no matter where the slices are, those are symmetric with respect to the x-axis, right? So instead of saying like it's the very top minus the very bottom, I could just say that it's, well, sorry, the top minus the bottom gives us the entire length of this. And since we want the radius, what do we need to do? Yeah, to divide that by 2. So we're after, we'll call that R1 for radius 1. You know, like this right here, we could call like R2 or R whatever. Okay, so the top minus bottom would give us the diameter. We want the radius, so we have to take half of that. Okay. Or we could just say, since this is the radius, right here, this is the radius of that particular cross-section, I can just say it's the top minus 0, right? You can say, here's the line 0. So if I just take this minus this, and then I get the length of the radius for that particular cross-section as a function of x. So does that make sense, what we've put there? Anybody have any questions? All right. Okay, but what is this top part of the function, or the top part of the circle? I don't know if I can do. Oh yeah, maybe. See how this works. All right, it's not great, but better than free-handed. So what is this? What is the equation that describes this boundary right here? Or what is the equation that describes our entire boundary, that full circle over there?
X squared plus y squared equals...
Yeah, right, it's just a circle, radius capital R. So this is x squared plus y, centered at 0, 0. X squared plus y squared equals to capital R squared. So since we want that in terms of x, we have to solve it for y, right? We only want to see x's involved in that function. Okay, so the top half of the circle, if we're using that to determine the top minus 0, which is the radius, the top half of the circle is the positive root, or where y is positive, and then of course the bottom half of that circle would be the negative root. So there we go, there's the top minus 0. So that's what our radius or radii are anywhere along or inside of that circle. That is each radii square root of capital R squared minus x squared. So now we have R, like we said here, we have R in terms of x, and then we're ready to work back with the area of the cross-section function. Thus, the area function of x is pi times r, which was this, squared. I'll write that here. Okay. Which is good for us because now we don't have to integrate a square root. We have pi times capital R squared minus x squared. That's our area function. The area of each cross section. Okay. Any questions? So then in order to compute the volume, we're just going to integrate our area function. With respect to x. And then the bounds on x are just the bounds of where our cross-section runs from. Each slice ranges from where to where? Negative r to positive r. So that's up there in that picture of the circle that we drew. All of our slices run from this way, from negative r to positive r.
Couldn't you, again, do symmetry, 0 to r?
Yeah, exactly. That's what we'll do, make it easier too. So again, utilizing symmetry, we're going to say that I'm going to pull out the constant pi as well. If I go from 0 to capital R, I have to double the integral. So I'm going to double that, and I'm going to pull out my pi from here. So 2 pi integral from 0 to r of capital R squared minus x squared with respect to x. And then that's what we'll compute. Totally fine if you want to compute from negative r to r of what we have here. You'll get the same result. Okay, so integrating r squared with respect to x, what do we get? Do what?
R squared x.
R squared x, so I'm going to put that in here. That's r squared, it's a constant. Integrating a constant. Minus x cubed over 3. and then we're evaluating from 0 to R, to capital R. And, you know, if you don't want to get confused, just remind yourself that these bounds we integrated with respect to x, so this isn't, these are x values. Those are going in for x, not R. Okay, so see, when we utilize symmetry, the nice thing here is this, the bottom limit plugged into our antiderivative, it's just 0. So it makes the computation a lot easier. So we have then 2 pi. Rn for x, we have r squared times capital R, so this is r cubed. Minus Rn for x here, we have r cubed over 3. So, you know, there's our antiderivative at the upper limit, and I'll just put here at the lower limit it's 0. So we have 3r cubed over 3 minus r cubed over 3. So we have 2 pi, what's in brackets, 2r cubed over 3. And then we just multiply across the top. We have 4 pi. Huh?
At the top, and then be 4r cubed.
No, because it's 3r cubed over 3 minus 1r cubed over 3.
Sorry.
And we get the 4 by multiplying this 2 from the 2 pi we pulled out. 2 pi,
Yeah.
that's 4 pi r cubed over 3, which is what we were after. So check out, we derived the area of a sphere using calculus. Or sorry, the volume of a sphere using calculus. And all we had to deal with were the areas. I don't know, I think that's pretty cool. Yeah.
In a test, if you left it as just 2 pi and then parentheses r cubed minus r cubed over 3.
Yeah, here.
Yeah.
So if you just stopped there, yeah, I mean, it's still correct. I would say that those elementary operations shouldn't just be left alone, that you should just carry them out. It's neater, helps me out, it's more traditional, and it's not difficult. So, you know, if it were like this super complex expression, then I would probably be okay with you leaving it. Any other questions on that? So that's the general slicing method that helps us obtain volumes. Now we're going to turn our attention in the rest of 6.3 and in 6.4 into how do we compute volumes that are generated by taking a two-dimensional region and revolving it around an axis. The idea of what we've just done here in these last two examples is what we're building off of. So that doesn't change. It's still like the fundamental baseline that we're dealing with. So here's kind of what we're working with. We're going to say, let me look at a function f of x on some interval from a to b. And then I'm going to specify, take that particular region, capital R, and then rotate it around an axis. So if we take this region and we rotate it around the x-axis, then we get this kind of, I don't know, bell shape. And we're going to be asked to find the volume of that bell, or whatever that figure is. Again, the idea is based off of the slice and sum approach. So we're going to focus again on one slice through here. And then it's really helpful, I think, at least at first, to visualize this. So that's going to be sort of over here close to A. And think about that as a really, really thin rectangle. Notice the axis we're revolving it around is the x-axis. So then you got to envision in your head, like if I take this really thin rectangle, let's just say it's your pencil. If you take that and rotate it around, what shape does it make? It makes a circle, right? So, and that's crucial to the two varying methods we see in 6.3 and 6.4. So I know it's down below, but perhaps it will help to look at it this way. So there's our rectangle. Let's see if I can do that a little bit. Okay, so there's our rectangle in that particular region, and we're going to revolve that around, oops, wrong one. We're going to revolve that around some axis. Here we're revolving it around the x-axis. Again, we're focusing on just that one rectangle because all of the other rectangles will make the same shape when they're rotated. Okay, so then that's what we're kind of dealing with, and we're going to put that together with what we just talked about with the area of the cross-section. So the idea is that we've taken this rectangle, we revolved it, and what it has generated is a circle, or here referred to as a disk. So then we say, well, how do we find the volume of that figure? Well, we just integrate the area of each cross-section, which we now know is a disk, times dx or dy. That's kind of, I'm just going to put it here. That's that blue cross-section that we're looking at. And now that we know we're dealing with cross-sections that are circles, then we ask ourselves, what's the area of each cross-section? It's just pi r squared, where this distance is your radius. So here is the radius of that particular cross-sectional circle. Again, since the function varies, we know those radii will vary as we go from A to B. So then we're back to the question, how do I measure that distance? How do I measure r with a vertical element? It's just the top minus the bottom again. That hasn't changed. Here, the top is f of x. The bottom is 0. So the radius is just f of x. So it's pi times the radius given by the function minus 0, pi r squared. That's the area of the cross-sections. And then we just throw that into our integral and we have the volume. That's the area of each disk or circle. Okay. Does anyone have any questions on that? So this is called the disk method because you're integrating a bunch of disks times the thickness to get a volume. So this disk method and the next method in 6.4, they're specifically dealing with volumes generated by revolutions. The previous two examples that we looked at didn't involve any revolution. It was like, here's your boundary, your cross sections are triangles. What kind of volume does that make? I think those in a lot of instances are a little bit harder to picture than these here. But if you can kind of get a grasp on, what the image will look like, specifically what happens to your rectangle when you revolve it this way or you revolve it this way, it will totally help determining which method to use. If you're bad at visualizing stuff, that's totally fine. Just remember the disk method is this, the other method is something different. Just have to remember that. Okay. So for instance, let's take the region to be what's bounded by e to the negative x, y equals 0, x equals 0, and x equals natural log of 4. And then they'll specify to which method to use. So it says use the disk method. So, what I like to do is say, all right, well, I'm going to use the disk method. I just like to remind myself that I'm dealing with circles, pi r squared, or, pi times f of x squared. To find the volume of the solid generated when it's revolved about the x-axis. So let me back up again. And notice that those disks are generated when the rectangles are perpendicular to the axis of revolution. Maybe you've seen before, or you can see in your head, what happens if my rectangles are parallel to the axis of revolution? Well, then I get a completely different figure. I don't get this circle anymore. Okay? So get it in your mind that when we do the disk method, our cross sections or our rectangles, they are always perpendicular to the axis of revolution. Perpendicular to the axis. Oops, I don't know what I'm doing. Not the x-axis. Just to the axis of revolution. We'll see in 6.4 what happens when you rotate parallel to the axis. But disks are always perpendicular to the axis of revolution. So here's our e to the negative x. I guess I'll do all this in red. X equals to 0 is here. Y equals to 0. And natural log of 4 is here. Remember, we want the region that's bound by all of the things specified. So I know sometimes it's hard when you have, like, especially when you look at a picture and there's like, well, which region is it? Is it this one or the one over here? It's got to be common to all. So we're dealing with this area here. And so really, like I said, it depends on how you're going to remember this, but you do have to remember when they say use the disk method or when they say use this other method that we'll talk about in 6.4, you have to remember the structure. Is it pi r squared? Is it 2 pi r times something else? So that's something you just have to remember. And if you forget, then that's where drawing these rectangles and saying, well, I'm rotating about this axis. If I rotate this about this axis, then I'll have this thing. Which is a circle. And then you kind of have to like default back to the, what do we call that? That cross-sectional area stuff. This whole thing is being filled up with circles. Area is pi r squared, right? So we can sort of get back to it that way as well. Or, like I said, you can just remember the disk method is pi r squared. So what is r? E to the negative x, right? Because here's our circle. We've revolved it around the x-axis. This is the radius of the circle. So from here to here is the radius. Again, how do we measure that? Top minus bottom. It's the function e to the negative x minus 0. Top minus bottom, which is e to the negative x minus 0, which is e to the negative x. So then we have r over here, but let me just write it here. To be specific, those all vary, determined by that function of x. So this f of x that we're integrating, we have it, it's just e to the negative x. So we're going to say we fit it here. We're gonna say the volume is the integral of the areas of each one of these circles, pi r squared dx. What are the bounds on x? Right, 0 for this rectangle here, all the way up to this rectangle, which is the natural log of 4. So that's the setup, that's it. That's how we compute the volume. Of course, we've got to integrate that, but that's really step one. That's what we're after. Does anyone have any questions? Okay, what's the antiderivative of e to the negative x?
Negative e to the negative x.
Yeah, I'm going to pull out the constant antiderivative of e to the negative x, negative e to the negative x. Sorry, we kind of got a little too antsy here. You're right, the integral of e to the negative x is negative e to the negative x, but I have to square this. Okay, so we square e to the negative x. Sorry about that. We need to integrate e to the negative 2x. Yeah, so pi is out here. Remember, these are with these linear arguments, mx plus b. Those should be remembered. Otherwise, you have to go through the u substitution process. Put that here in brackets again. So that's e to the negative 2x divided by, or times what?
Times 2.
Times
Negative 2.
Close, it's negative divided by negative 2. Or negative 1/2 times that. From 0 to ln4. I think that's on the integral table from 4.9, but it's the antiderivative of e to the ax is e to the ax over a. No, plus c, I guess, technically. So really, I would just remember that. Otherwise, you have to do a u substitution, and there's nothing wrong with a u substitution, but you know, if we're trying to maximize or make these things a little bit more efficient, then u substitution for these linear arguments isn't the most efficient thing to do. So you might see that handout from 4.9 for those. Does everybody remember u substitution?
Yes.
Maybe. So here, let's just look at it this way. I'm going to say let u equal to negative 2x. We have to account for the differential too. We've only accounted for this thing. So u substitution always then involves taking the derivative of your substitution. We're saying, really remember, it's the derivative of u with respect to x. And we say that's negative 2. But generally when we write it, we just say du is negative 2 dx. Right. Well, we only have a dx here. We don't have that negative 2. So we're going to put that negative 2 over here with the du to account for that dx. So then that negative 1/2 du was replacing the dx. And e to the negative 2x is e to the u. So then really the way we looked at that was we said, well, that negative 1/2 is a constant. And then we can just integrate or find the antiderivative of e to the u with respect to u. So it's just e to the u. There's our negative 1/2, or division by negative 2, and there's our e to the u. So sorry if that seems elementary. If it's not, for sure you got to look over those things. All right, let's plug in. And just be careful when you have exponentials, rather. I've seen some people think that just when you plug a 0 into an exponential, it just disappears, but that is never the case. So just be careful. We have pi. We're going to plug in ln4. And what I'm going to do before I plug this stuff in, remember this is x and this is x. It's from 0 to ln4. That negative 2 is just another constant. So I'm just going to pull that out here and say it's negative pi over 2. And just evaluate the e to the negative 2x from 0 to ln4. If you want to keep that constant of negative 2 in both of your computations, again, that's totally up to you, but just leaves, I think, more room to mess up. It really is just a matter of preference, though. Okay, I'm going to go down here. And so what do we have? We have negative pi over 2. We have e to the negative 2 ln4 minus e to the negative 2 times 0. What's the e to the negative 2 times 0? What does that give us? What's the easier one? 1. What's e to the negative 2 ln4?
Is it 1/8?
Is what?
1/8?
Not quite 1/8.
Or 1/16?
1/16, yeah. So if you have a calculator, you just do that, and it tells you what it is. But you remember the properties of logarithms? The multiplier of the logarithm really can come up to the power. So that's, that's coming up here, like that. And then we say that's the same thing as ln of 1/16, right? 4 to the negative 2. But since it's e to the ln of 1/16, it's just 1/16. So maybe your calculator does like exact answers. Some people's calculators don't. So, you know, depending on your calculator, you might need to remember this stuff too, because a lot of the things will say write your answer as an exact value. And so we need to keep it exact. We wouldn't want a decimal approximation for this. Okay, so we got 1/16 minus 1. That gives us a minus 15/16. And so that gives us positive 15 pi over 32. And that's the volume of that region revolved around the x-axis. Does anyone have any questions? All right then, so how about you all give number 4 a shot. Do it the calculus way, and you can verify the easy way. So let's get the easy way out of the picture. We have this particular region bounded by the two functions there, or the two function and the line. Use the disk method. So I see this, I'm immediately going to think this. To find the volume of the solid generated when it's revolved about the y-axis. Remember, disks are perpendicular to the axis of revolution. And maybe we can talk about setting this up just so we can get the easy way out of the picture. So you're not cheating. Okay, so we have, how do we graph x equals root 25 minus y squared? What is that? The semicircle. Which portion of the circle are we showing? Yeah, so not the top half. Remember, the top appears when y is positive. This is x is the positive square root. So x is positive over in quadrant 1 and 4. So we have that semicircle. What's the radius of that? 5. So this value is negative 5. Positive 5 and positive 5. Okay. So really that's step one. When they give you a region, you want to draw it out. There might be some people that are able to, do some of these without drawing the figure. You can just kind of think about what's happening after you've done a few of them. But I would seriously recommend drawing these regions out. All right, so there's our region. We're going to say I'm taking that region and I'm revolving it around the y-axis. So if I'm revolving it around the y-axis and I have to use the disk method, my disks or my rectangles or my cross-sections, however you think of that, they have to be perpendicular to the axis of revolution. Okay. So those rectangles or those cross sections or those disks, they have a tiny thickness in the y direction. So we have to integrate with respect to y. Okay. So maybe with that in mind, what's the easy way to compute this volume? It's just the volume of a sphere, right? If I take that semicircle and I revolve it around this axis, doesn't that generate a sphere? So I don't know if you can see that in your head or not, but I'm not going to attempt to draw it because that would be abysmal. So let's just get that out of the way. This is the easy way, I guess. We just compute the volume of the sphere. It's 4/3 times pi, and the radius of our sphere would be 5. 4/3 pi times the radius cubed. You should say that's the volume. So what do we have? 125 times 4. So the volume of that sphere, the easy way, I guess, is 500 pi over 3. So now use calculus and see if you all can get 500 pi over 3 using the disk method. So take about 7 minutes. Yeah, that's right. Okay. 0.005, yeah. Yeah. Yep. All right. Oh, nice. Okay. Cool.
Because I need 2 extra credits to graduate.
Oh, all right.
Some way to platform, and it's like it's less competitive.
I like to think
It's
about
fun.
it like that.
It's actually used to play a whole lot of frisbee golf. I really haven't done that much, but that was like really low key. Just throwing frisbee.
Right.
Cool. Keep going. And you're outside, and it was cool. Okay, so 7 minutes. Okay.
what I tell
So,
Alright.
the,
Just like it was.
it's, and then this part right here, actually the whole thing. Negative 5.
Right, that's just like the whole area these things.
Yeah, that's how you said
Oh, okay. Okay. Well, as long as you understand it, cool.
And then,
well, that's all you have to do is figure out that you're set.
that's just like this area.
So this area right here, that whole thing is what right here is or, well, so the
What time did you
this
go
is
to?
the one, right? That part? No, this would definitely, this right here. One slice. So this second one here, that, this other rectangle.
Yeah.
And that, we're just going for all the different slices. That kind of makes sense.
Alright, well, yeah, I understand, like, this is that, but I thought the integral, you just like the integral full face, you know, that area, exactly, I thought this part of this part of it.
You're right, and then we're supposed to take an area, but
It's irrational, like.
so we're deriving with respect to dy, correct?
Yeah.
Which means that we are taking slices this way.
This way is
So we're finding the area, 3D space, so imagine a sphere, right? Normally, we should take the area. Yeah, right. Square. We're taking the area perpendicular to what we take, which makes it a 3D going around axis. We're taking an area.
Okay, wait, so you're saying like, if
We
you,
already have an area right here. The area up to a ball.
yeah, I'm just, oh, okay. So an integral makes like the 2D area, like 3D area.
So,
That-
don't get me wrong, if you had this right here, like, you know, just how you have that,
It's not the first
your
one.
areas, what you would find, but since we have those squares, I know we're
I mean, it was a good time.
Okay.
That was really.
So, oh, okay, so this is the area base.
So that's.
Well, this is not the full circle, the base is,
Literally, that's
Should be the full circle.
If you plugged in any
Any down through
Y
the
value,
campus. Which is not fun, you know, for hands on the cover.
it's hard to explain. For now,
You
just.
ruined.
I'll explain.
I was Alyssa.
Just take that word. I was actually out asking.
The bartender gave me a friends like a discount. This is so nice. For each class.
Memorizing.
Because I started that one. No, that's fine.
I really just wish that was like He's very special. I got another What now?
So, just, make that square root,
Why is it easier to carve pencils than
Yeah.
I don't know. It's like a scam. But it's not different. Like just because you're using this.
Right, yeah.
Okay. Like that, I seems about like
Yeah.
this much.
Yeah, you did.
Should be.
The more you talk to the theater,
Is it one doctor? It's so much easier.
I swear, just do the however long.
Oh.
We're taking, that's the derivative. We're looking for
Oh.
Two, yep. You guys, you have, right, because you got the tilt
How? You sounded really honest.
Oh, yeah, it was good.
Oh, it's hideous.
Next Tuesday.
I didn't know that. It's good. What's the scribble? What is that? What is that? What are you even doing? You erase everything.
All right, I think everybody had the right answer. If I didn't get to circle back around to you, I apologize. So there was some issues with dropping the 2. A lot of you did actually just calculate the volume for the top half of the sphere. So just be careful. That's usually I'll set it up fully. And then if there's symmetry, then I'll go from the the full version from -5 to 5, let's say, to the half and doubling the integral. So just be mindful of that. Okay. But overall, everyone did really good. I think some of this stuff is, it's a little bit wacky when you see it at first. It's hard to sort of orient things and. Is this dy, is this dx, what is this, like what am I doing? It's really hard to grasp that, and I think, you all did really well, so I'm proud of that. I'm proud for y'all. So then, we'll just go ahead and finish writing this out for those of you that I didn't get a chance to come back to. Y cubed over 3 from 0 to 5. Again, the nice thing about these kinds of, especially polynomials or other powers on x or y, when we use symmetry, that 0 is just going to cancel or zero all of that out. So it's basically like decreasing our workload by a half. So then we get 2 pi. We have 25 times 5 is 125 minus 125 over 3. It's 375 over 3 minus 125 over 3 gives us 250 over 3. So that's what we're after, 500 pi over 3. Does anyone have any questions on that? Okay. Well, we'll look at some more examples, and of course, this isn't the most simplistic, kind of disk we're going to look at. We'll look at a more general region. But I forget if we've got one more example maybe, or not, I don't remember. No, we'll look at the next method after break. So if there aren't any questions, let's take 10 minutes, and then we'll talk about the other method. All right, so the next method, think about that first method, the disk method, was when you first looked at areas using Riemann sums. Then in 6.2, we said, how do we find the area of a region bound by two curves? And that's kind of what leads us into this method here. So instead of having a region that's kind of nested against an axis and revolving it around, we're going to take a region that's bound by two functions, not necessarily nested against the axis of revolution, and then we're going to revolve that around a particular axis. So you got a little insight here as to what that looks like, but let's look at the interactive figure again for this one, not that one. And so this again is our cross section or our slice or our rectangle, and then we're going to revolve that around an axis, and then what we get here is a washer. They're going to call that a washer. So we're dealing with a washer method. So when we see the formula, where it actually comes from is it's right here. See. Let's do that. So that's our cross section once it's revolved. But note we have sort of this large or outer radius we'll call capital R. And then we have this inner radius we'll call lowercase r. So again, to find the volume that's generated once that's revolved, all we need to know is what the cross section actually looks like in terms of its area. So the area of this figure here is computed by taking the area of the large or outer circle by pi capital R squared, and then just subtracting the area of the inner circle, which is pi little r squared. But just like in that last setting, the radii here vary, and they vary depending on the function. So here's, let's see if we can code this a little bit better. There's your f of x, and here's your g of x. Okay. That slice or that rectangle is that rectangle. But notice over here in this kind of two-dimensional setting, we do this in red. When we rotate, if we think about this revolving around the x-axis, then that's what's generating our outer radius or our larger radius. I don't know if I can do this justice at all, but I'll attempt to do so. So it kind of dips like that, I guess. And then this one we called g of x. So that'll be down here. Well, not technically to scale, but kind of like that. And then this rectangle is here, but that's actually making this
Yeah.
What?
Because that'd be the outside.
Red would be on the red would be
Yeah,
outside.
yeah, see. So much for my failed attempt. So that's generated through there with the outer function revolving around the x-axis, which gives us that complete circle, if you will, right? But then the gap or the deleted portion in the middle, that smaller circle, that's coming from this gap right here. When that's it's over exaggerated, but basically anything that's not nested against the axis of revolution is going to create that hole in your region that doesn't account for any area and thus doesn't account for any volume. But again, the outer radius, we're looking at this measurement or this distance. So here's my outer radius, and then my inner radius is from the bottom function to the axis of revolution. So that's my little r. Okay. So how this works out is then capital R, in the sense of F and G, capital R is the distance from F to the axis of revolution. So let's just write that out. Capital R, why does that? Capital R is the distance from the outside function to the axis of revolution. Another way to think about that is just from your axis of revolution, which function is furthest away from the axis of revolution? That'll give you your outer radius or your capital R. And then lowercase r is the distance from the inner function to the axis of revolution. So the function that's closest to the axis of revolution is how we measure the lowercase r, or the inner radius. Okay. So really the way you see that in terms of functions is that this pi is factored out. We have outer radius squared minus the inner radius squared. So that gives us the area of the disk, and then that's what we're integrating. Integrating an area times a length gives us a volume. I'm not quite sure if that's written out or not. I forgot to put that there. Okay. So the volume. This is the washer method. The volume is the integral from, wherever, a to b of pi times the outer radius squared. And we'll just stick with the figure that we have there. The outer radius is what we have up here. Yeah, the outer radius is capital R, but with this picture right here, what is the outer radius? Yeah. So pi times f of x squared minus the inner radius, which was the function closest to the axis of revolution, is g of x. And note the disk method is the washer method, where the inner function, or g of x function, is equal to 0. So this is the disk method, right? Really, we should say the disk method is just a special case of the washer method. So we'll say that. If g of x is 0, then we're looking at the disk method. Okay, so it's a little bit more complex. And the analogy here is what we did in 6.2. The analogy of what we did with the disk is from, Calc 1, just finding areas that way. So let's look at the region bound by y equals x plus 2, x equals 0, and x equals 4. And we'll use the washer method. So immediately I want to think of this here. To find the volume of the solid generated when it's revolved about the x-axis. So let's draw this region. So y equals x, y equals to x plus 2. Let me get this parallel. X equals to 0. And x equals to 4, so somewhere over here we'll say that's x equal to 4. So the area common to all 4 of those, and is this area here. And then usually it's obvious when you're using the washer method, right? Because if I have to revolve this about the x-axis, we see there's going to be some gaps. Maybe not here at the point at the origin, but everywhere else, that's going to generate that inner circle of the washer. So all of this rotated around the x-axis, that's where we get that empty space. Let's do this way. So the washer and the disk method, since the disk method is just a specific version of the washer method, the same thing is true about our cross sections. They're perpendicular to the axis of revolution. So we're revolving around the x-axis. Our cross sections then will be rectangles like that with a small thickness dx. So everything we do needs to be in terms of x. All right. So then our capital R, how do we find the outer radius of each one of these washers? What is the outer radius? X plus 2, right? The function that's furthest away from the axis of revolution will be the outside or the outer radius. So let me just label that. The distance from here to the axis of revolution is capital R. Again, that's this thing. We measure that top minus bottom. Top minus bottom. Top minus bottom, let's just say that. Top minus bottom. Function x plus 2 minus 0. Which is just, we'll just say x plus 2 over here. Okay. Lowercase r is then what? X, right. The function that's closest to the axis of revolution is this one here. So that's going to be our lowercase r. Again, top minus bottom. 0 or just x. Okay. Then we just fit it into the form for the washer. Pi outer radius squared minus inner radius squared. Pi times the integral, our outer radius squared minus our inner radius squared. So that's x plus 2 squared minus x squared. And our bounds on x are from where to where? 0 here, all the way to 4 here. 0 to 4. Any questions on the setup? So here I'll just say expand, combine, and then all we're doing is integrating powers of x. So that should come out to be 48 pi. Okay, any questions? All right, let's take, I guess, well, we gotta do 6-4 as well. So just take about 7 minutes for this one, and if we're not finished, then we can finish together. But we try to set up and establish what you can do in 7 minutes.
Oh.
I distributed, so it's just one square. Because the one is 4, the one third goes down, makes it
I just did that from the start. Or is this? You have to distribute, you can't leave power out.
Yeah. Because just the square just means this thing times itself.
Yeah, you could do like a use.
I am like 3/4 of the way through the very
Or
first
you could
one,
say, well, that's just a
so
linear, one half, that's just one.
like 4 left. Yeah.
1/4 y squared.
I think it's easy just to.
Y squared.
Yeah, I thought it'd be like only 11 problems. Thought it'd be done fast.
So
but
yeah,
they
kind of just put it. Yeah, I had to square that. I got a lot of line, I just watched that board.
Well, okay, I did.
Too busy this weekend.
Like, add one to
Oh, no, that's what it's easy.
It wasn't a whole term.
Yeah, so
Okay.
Coding.
Starts rotating.
Well, yeah.
Tip, and it's like rotating. Yeah. 5. That's probably
If you yeah, it's like
Yeah, except like the problems are just like.
would
just be like.
So like an intro question, so that's basically like an overview.
Oh my god,
Plus, then like taking out.
you got right that one
So it's
time.
like we have the ABC class, so a lot of those count.
Well, that was just easy.
It was interesting.
So for fractions, the parentheses are squared, yes. Great. That's so good.
Basically just set the base area.
Further down, not.
No, it's a vertical stretch. So you take y equals x and stretch it up vertically. It's got a steeper slope. You got a line with slope 1 versus a line with slope 2. It's steeper.
The very end was specific blocks there, and it would shut down. I had to put like a header, I think. No, it's just a graph. Triple guessing my header.
Yeah, all right, so hello? Let's bring it back. The main thing is setting this up and then looking at your problem and saying, okay, well, I'm going to revolve this region around the y-axis and I'm using the washer method. So these cross sections, washer needs to be perpendicular to the y-axis. So here's my y-axis. My slices need to be perpendicular to my axis of revolution. And then, just exaggerating this rectangle a bit, we have those things as thickness dy. So we have to integrate with respect to y. Okay. That's really the first part. The second part, once you figure out the region and what you're integrating with respect to, is to remember the formula for the disk or the washer. And we fit the functions in for capital R and lowercase r. So we have the volume with respect to, I'm going to pull the pie out again, with respect to y. So our bounds need to be in terms of y then. Our rectangles run from here all the way up to here. So y value of 0 to y value of 6. The outer radius, and this again is where like graphing is important, right? If you have these flipped, then you're going to say the outer radius is y over 2, so you have things reversed. But the outer radius, remember, is always the function that's furthest to the axis of revolution. So that function is y equals to x. So here's our outer radius squared. We subtract off our inner radius generated by the function closest to the axis of revolution, which is y equals 2x. We want it in terms of x equals 2 or y, so it's y over 2. Inner radius, and we have to square that. So there's outer radius squared minus inner radius squared times pi. So it's easier to multiply this out. This is y squared over 4 power rule. Or you could combine the y squared over 4 with the y squared and just integrate one term, right? So it doesn't really matter if we combine these two things, this thing and this thing from here. You can integrate both of them, totally fine. So you should get, what was it, 54 pi?
Yep.
So I just kind of want to focus on the setup at this point. Were there any questions on this? All right, then. Last example here, and again, this example will kind of show us another reason why symmetry can be useful. Okay. So the region bound by the absolute value of x. So let's say this, and we'll do that in red. And 2 minus x squared, which is our parabola. It's facing down, shifted up 2 units. So we'll just say that's here, shifted up 2 units. And it's facing down. You get that? No. I'll try to do better. Okay, good enough. All right, so the region bound by the red and blue curves. Use the washer method to find the volume. So again, I'm thinking pi times outer radius squared minus inner radius squared. To find the volume of the solid generated when it's revolved around the x-axis. So we're revolving around the x-axis. My cross-sections for the disk and washer method need to be perpendicular to the axis of revolution. So those have thickness dx. So I guess there's two ways to approach this. One way, if we use symmetry, we don't have to utilize the definition of the absolute value. The other way, we can use the definition of the absolute value, but it involves then us finding 2 different points of intersection. So does everybody see that I drew this horribly, but this is symmetric with respect to the y-axis. So we can just look at that half and then double our result, right? So I guess we can address either way. So say we're not utilizing symmetry here, then we have to find these points of intersection. Do we know those just by looking at it? No, so we have to figure that out. The thing is with absolute value, you always have to work with a non-absolute value to actually work with an absolute value, right? When we saw with distance traveled, we had to get rid of the absolute value to work with it. It's the same idea here. This function, if you forgot, was defined piecewise. So if we're going to use the absolute value, we have to say that this is x over here in the first quadrant, but it's y equals to negative x in the second quadrant. And then say, all right, well, let's find the intersection. In 1, we'll look at the intersection in quadrant 1. So for quadrant 1, then our absolute value piece only becomes y equals to x. So we want to know where does x equal to the quadratic, right? So we're going to say where does x, let me just do this in color here. Where does x equal to our quadratic? And so you've got a quadratic to solve. We have when x squared minus, x squared plus x minus 2, rather. When does that equal to 0? Yeah. What's that, right? So that happens when x is -2 and when x is +1. Which one is true for us? It's just 1, right? Because we're in quadrant 1. This one doesn't make any sense. So that's an x value of 1. Sorry, quadrant 2. Yeah, we're in quadrant 1. So that's an x value of 1. And now maybe the symmetry can help us out with the other one. But let's just go ahead and work through that other one as well. Because we're approaching this through the lens of not using symmetry. For now, anyways. So quadrant 2, we have to figure out, again, where our quadratic is equal to the absolute value in the second quadrant is defined as -x. So that's when x squared minus x minus 2 is 0. So we have x minus 2 times x plus 1 equals 0, which means that x is 2 or x is -1. Again, we're in quadrant 2. It doesn't make sense to say +2. So it's -1 as that other intersection. Okay. So now that we have those values established, then we can set up the integral for this volume, right? We would say, all right, well, I'm rotating everything around the x-axis, so I have to look at it as two separate pieces added together or put together, right? If I'm not going to utilize symmetry. So the first thing I need to look at is, all right, well, what happens when I take this region What happens when I take that region and revolve it around the x-axis using the disk method? So that'll give us one volume plus the other volume generated by this thing. So we're going to revolve around the x-axis, revolve around the x-axis. Right, so we have to take this volume plus this volume if we're not going to utilize symmetry. So you've got two different washer method setups here. That would be the volume for this one. We'll just call it volume 1. Volume is pi, outer radius squared minus the inner radius squared. Okay. So in this figure to the left, our outer radius is what? 2 minus x squared. It's the top function, which is our quadratic, down to the axis of revolution. So that's 2 minus x squared. So outer radius, 2 minus x squared, squared, outer radius squared, minus the inner radius squared. And our inner radius was determined by what? Negative x. That's negative x. Y equals to negative x. I should have wrote smaller. See if I can scoot that. All right. But again, that's going to give us the volume of just that half of figure. We have to add to that the volume here, which is very similar. And then well, let's talk about the bounds here on x, or from where to where on the first figure. from where? -1 to 0, -1 to 0. And then this one will go from 0 to +1, pi times the outer radius squared. Get all this here. Outer radius, again, is from the function furthest to the axis of revolution. So that's 2 minus x squared. Squared. Minus the inner radius. Squared. Over here, the inner radius is determined by y equals to x. You see they're the same thing, right? It's just we had to split that up. You know, if we, it's because the square is here, but the outer radius, or sorry, the inner radius in each case is different. This is positive x, and this is negative x. It's only because we have to square those that would sort of get washed out, right? So that's certainly one way to approach it. It's more convoluted. There's nothing wrong with it. Does anyone have any questions on that setup?
You said that's in thinking of terms of not symmetric.
Not symmetric, yeah. We're not utilizing symmetry here. So then here we'll say, all right, well, what happens if I utilize symmetry? Well, if I utilize symmetry, then it becomes a lot more, I guess, efficient. In the sense we have this thing, we know it's really two of those. So all we have to do is say the volume is two of these, pi times the outer radius squared minus the inner radius squared. Nothing changes here. We're working with the positive x in the first quadrant. So there we go. The bounds for this particular piece are from 0, as we found, to 1. So then you don't even really have to think about, you know, the working with the two different pieces of absolute value of x if you do that. So questions on either one of those setups? The most important thing is being able to set those up. And so we need to FOIL this out, expand and combine all of this stuff. And they're all just, we're integrating a polynomial. What is it? Gets sort of, you know, it gets sort of tedious because you've got fourth powers, you know, like it's just time consuming to evaluate that, but you should be able to, if you're revisiting this, you should get it to come out to be 76 pi over 15. Like I said last class, if any of these that we sort of just, you know, set up and then say this is the answer, if you have any issues with those, please feel free to email me. I'll be happy to go into detail. Yeah. Yeah. Wait, does it have problems on AML? Is that what you're asking? Yeah. Yeah, so my math lab will have a problem similar to this. Might have other symmetry that you could utilize too, but yep. Any other questions? So that's the disk/washer method. Last page is a summary. Okay, include anything else. All right, so I also wanted to point out the non-symmetric approach we took to find the volume in that last example. There is another piecewise function in your homework. I'm not sure exactly what it looks like. You know, it's maybe something like this. It says, you know, these separate pieces are defined. And then it says find the volume of that region when it's revolved around a certain axis. So you just want to treat that like we treated the absolute value without symmetry, because this doesn't have symmetry. You know, so we'll say, all right, well, this piece I'm going to use the disk or washer method and integrate from 0 to A. This piece, disk washer method, integrate from A to B, and then, you know, whatever, this other rectangle from B to C, and this triangle from C to D. All 4 of those are washer methods, and you would just add it all up. And if you get there and you have no idea what to do, just email me or ask in class, and we can sort of look at it, work through it maybe if we have time. Okay, I do want to start 6-4. We've got about, what, 6 minutes or so? But in continuing with this notion of, taking something and revolving it around an axis, here with the shell method, what we're going to do is say, all right, well, we have this region. What happens now if I take this rectangle and revolve it to the axis that's parallel? So I'm going to revolve this around the y-axis. I don't know, you can kind of see that here, but what we're getting, I'll just say this. I'll have this. You got to envision that this is a solid here. I like this thing. This is not quite a disc, or, it's a circle. As we call them, I guess they call them shells, but it's so not a disc or a washer anymore because it's not flat. What we're getting is this cylinder, this hollow cylinder, basically. So we're gonna, sometimes they refer to them as the cylindrical shell method. But nonetheless, when you take a rectangle and you revolve it around an axis that's parallel, you will get a cylinder or a cylindrical shell as opposed to like a flat washer or a disc. And basing our work again off of 6.3, the cross sections that we generate, cylinders or discs, determine the rest of the problem for us. So we have, here's the kind of basic morphology of it. We look at the sort of crude approximation, and then we let the number of those cylinders go to infinity, which turns the sum into an integral, which gives us the exact volume of that figure. So you can kind of see the formula listed there already, but think about it maybe this way here. If I take this sheet here, it's got a tiny thickness. But where that came from is, sorry for my cylinder, it's kind of crummy. If I just cut this cylinder and then unfold it, right, then I have like a flat piece of paper. So we can look at, well, what's the area of this right circular cylinder? We can say, well, how does it translate to this right here? Well, this, if we're going to measure that linear dimension, would be what? What? 2 pi r, because it's just the distance or the circumference of that circle. So there's the circumference of the circle, and then we'll just call this h. This is the height of the cylinder. That didn't change. That's still h. So the area of our cross sections, these right circular cylinders, are just 2 pi r times h. So that area . 2 pi RH. Those are the areas of our cross sections, right? And so then we need R and H in terms of X or Y, depending on how we're integrating. Okay. Does that make sense? That's where the 2 pi comes from. Now let's stay here and address that. I'm taking this thing and I'm rotating it around this axis to get these shells here. So we need R in terms of X and H in terms of X. I'll do those in different colors. Okay. So I think it's probably easiest to determine what's the height of this particular shell. Well, the height of that shell is given by this dimension right here. That is H. So how do we find the height? Yes. Right, it's just the distance from the function to the axis, f of x minus 0 again, or f of x. So that height varies, right? So if I had, this height versus this height, totally different, but still determined by this function. Okay, how about the radius, r?
dx.
Is what?
Dx.
Not dx, you're close, but remember dx is just this thickness of this cylinder. Remember the radius here for this particular one would be, what do we do in blue? So the radius is just the distance from my rectangle to the axis of revolution. So that distance is r. Does everybody see that? That's a spitter. Right, so like if this is my rectangle here and I revolve it around the y-axis, that's the radius of that particular cylinder. So here, oops, there's the cylinder, but we're just looking at half of it determined by the, so this thing right here is r. Does that make sense? Can you just see that in your head? Maybe. Well, it's when we ask the question, how do we measure that? We usually say it's the right thing minus the left because it's running this way. But in this instance, this is just some x value. Like if I told you this is an x value of 5, then I know the radius is 5. If I was here and I said the x value is a, then that radius right here is just a. So we're just going to say the radius is just whatever this measure on the x-axis is. It's just x itself. It's not a function. I mean, it is a function rather, but it's not this function like, x squared or sine of x or whatever. It's just x itself. So that's our r and h in terms of x. And then that's what we see here with this integral from a to b, 2 pi x times f of x. That's 2 pi times the radius times the height times dx. That's what we're dealing with there. So I'll write it over here. I know that's really small. Integral from a to b, 2 pi times x times f of x dx. This is our 2 pi times r times h. Okay. So let that sink in, and then we'll start working with examples using the shell method. I'll see you all Thursday.